Now I'm going to explain what the state machine is and how we can use it for the robot control. This is a table of contents. Today we are going to deal with PyTree to implement the state machine with the ROS. First of all, let me explain what the state machine is. So the state machine can define the state and its transition. So let me explain. Suppose we have this scenario. We have robot here, right? And this robot is going to find a sweet. In this case, it's a donut. So the robot has to search the location of the sweet. And once it identifies the location of the donut, it will move to the sweets and eat it. So in this simple example, we have two states, which is search and eat. And the transition is defined. So this is a criteria for to evaluate the transition. So once it's successful, it moves, and once eating is done, it will move back to the search position. And there might be some other criteria, which is to finish the operation. So maybe when the robot is satisfied for eating a lot of donut, it can finish its operation. So this is a very, very simple scenario, but the state machine is very powerful to describe the operation of the robot. And now we are working on the Robotics Dojo Competition 2025. And when you are looking at the game field, we have a lot of tasks. Starting from the weeding area, it will move to the ramp, basically the rough terrain. And once it passes, you need to load some items here in the loading area, and you have to navigate the robot, and finally you deposit. So there are several tasks. So, and mainly these tasks will be done sequentially, right? Like task 1, task 2, task 3, right? For example, task 1 is a weeding, task 2 is loading, task 3 is depositing. And you have to do it one by one. So in this case, you can simply define the sequence and identify the state and transit the state. So in this case, actually the Robotics Dojo Competition 2025 is advancement from the last year. Last year, the robot was able to implement the SLAM and the navigation. So we are going to add some other function, which is the state machine. So this is our intention. And to enable this, normally the ROS people, they are using a behavior tree.cpp. This is the most commonly used framework to achieve the state machine. However, when I looked at the behavior tree, it is implemented with the C++, and currently most of the teams are working with the Python, with the ROS. So I was searching the better way or the easier way to implement the state machine with Python. And I found that PyTrees is a good framework or the Python package, which can actually work as the same function as behavior tree.cpp. So today I'm going to explain the use of the PyTrees and its principle so that you can customize for your code, right? So here there is a GitHub repository for the PyTrees. And now I'm going to run some tutorial or the demo script. And for your information, I have also found a good tutorial. I didn't go through, but what I found is, so when you go to this YouTube channel, he is showing his sample script and he's sharing the GitHub repository. So let me open it. So there are 3 scripts, simple demo 1, 2, 3.py. So I think this is a good starting point for you to be able to understand the PyTree. So let's look at it. you can simply git clone this folder, robotics demos, and go to the PyTrees folder. I already git cloned, and here I have the code, simpledemo1.py. So I'm going to explain what it does. So to understand the PyTree, you need to understand mainly there are three types of composites, right? So starting from the sequence and the selector and the parallel. So mainly in this demo script, we are dealing with the sequence. This is the most basic composites or the state machine, right? And in the other example, so there are two types of Python package. The first one is a PyTree. Another one is a PyTree ROS. So PyTree ROS is a ROS implementation of the PyTree. So first we want to understand the PyTree and go to the PyTree ROS. And in the PyTree ROS example, we are going to use other decorators, specifically Eternal Guard, which is to monitor the event. But in this case, we are just focusing on the sequence. All right. So the sequence is going to execute some functions one by one. And most importantly, we have to understand each action or condition returns three states. So if it is success or failure or running. So in this case, the sequence is going to run the action or condition one by one. What is the difference between action and condition? So condition is something you want to use for checking the battery percentage, remaining voltage, or maybe sensor value, or etc. Like it's a small function, let's say, which can be done in a short while. And action is kind of a chunk of the behavior which may take time, right? So maybe you can understand it that way. But in the later example, we are mainly deal with the action. Condition is used for only monitoring the battery percentage, remaining voltage, right? And so what sequence does, so as written here, a sequence will progressively tick over each of its children so long as each child returns success. So basically the sequence is monitoring if all the child or children return success, 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 and success. All right. If any child returns failure or running, the sequence will halt and the parent will adapt the result of the child. So what it means is, so when the first function returns success, it will switch to the next function. And if the next function, in this case, action one, returns running, it will halt. So meaning it will loop executing the function or action one. And once action one returns success, then it can move to the next function, which is action two. Okay. But what about if action two returns failure? So if the failure is returned, the sequence will be stopped or terminated. So the action three will never be executed. So this is the point of the sequence. So let's see with the demo script. So I opened a simple demo one script. As I said, there are two type of sequence children. So the first one is action. The second one is a condition. Okay. And the main function is, so this is a Python main function, right? And this is just setting the debugging level of the logging. And tree equals make pt. So this is the main like constructor. And next one, it is triggering the tick once function. Okay, tick once is going to run some behavior once. So let's look inside the function of the makeBT. So makeBT is defined here. So in this case, first the root is defined as a sequence, okay? And name is defined as sequence and the memory equals true. Maybe you can look at the document, but when the memory equals true, this sequence is going to memorize the location of where the running is returned. So I was explaining that this action one or this action or condition can return either success or running or failure. So when the memory equals true, for example, let's say action, the guard returns success and action returns running. So when the memory equals true, so this the position when the running is returned is memorized. So the action one, so the sequence is going to memorize that the action one returns running. Okay, so in the next run, the sequence is going to go to action one because the sequence knows the action one returned running. So what happens memory was false? So if the memory was false, the sequence is going to see the guard because it just forget the action one returned running, right? Good. So let's go back to the script. And it's very straightforward. So there are three condition and actions. So the first one, the check battery, is using a condition. And there are three different actions defined. The first one is open gripper. Second one is approaching object. And the last one is closing gripper. So when you visualize it, it becomes something like this. So you have a main sequence, which is root. And first you check battery. And once it's successful, it moves to open gripper. And once it's successful, it moves to approaching object. And finally, closing the gripper. So you can imagine that this is a case for the manipulator, like you have some robot, right? You have some robot. And first you have to check the remaining battery voltage. And then you move to, for example, you have some target object. So the robot starts moving and suppose, okay, you don't need to move. In this case, you have some already target is here, right? So in this case, you already have a target. Now you want to open the gripper. You want to open the gripper first. You open the gripper, then you slightly move your robot, right, to approach to the target. And finally, you close the gripper. In this case, like this, yeah, to hold the object. So this action will be done sequentially, like open, approaching, closing in this order, right? So let's see by running the script. So here I'm going to run the Python script. Yeah. So what is done here is first sequence is ticked by the tick once function, okay? Tick once function. So sequence was ticked. And then you find a check battery operation, right? So this is a condition. It is not the action. And you can see the status change from invalid to success. So this function is defined here. So in each action and condition, actually the implementation is almost the same. So in this case, the battery checking is done under the condition. So let's look at it. So in the initializer or the constructor, you can initialize the argument, but this doesn't have it has only one argument, which is a name. So you can initialize a name with the first argument here. And then the first two function is actually triggered, like the setup and the initialize. So when you look at it, under the check battery function, first initialize function is triggered. Right. By the way, only the initialize function is triggered, and I don't see setup function. So maybe this we need to examine it later. So, but for this case, for now, you can just focus on the initialize function. And as you can see, the condition initialize check battery is printed because you see the check battery this is the first argument. So this will be substituted here. That's why you are seeing the check battery here. And then the next function is the update. So this update function is always consistently triggered, like in the Arduino loop or it is the Arduino loop function, something like it. And during the update function, self-logger debug condition update. So this is the message you will continuously see in the loop. As you can see, condition update check battery. Maybe I can slightly make it bigger. Yeah. In this way. Oops. Yeah. So I was explaining. Maybe I can run it again. Yeah. So what you're seeing here. Now I was explaining the upgrading. Yeah. Upgrading. So you are seeing upgrade and the sweep one. So it is sweeping for 1 second. And then it returns success, right? Then once the success is returned, what happens? So this function is over. So this function is terminated. So that is why you are seeing the terminate message, the terminate message here, right? So this is the first function check battery does. So let's move on to the next, which is the open gripper. So under the open gripper, this is an action. So let's go to the implementation of the action here. So this is very similar. You have setup, initialize, update, and terminate. And the implementation is completely the same. So as I said, the check battery, before I forgot to mention something. So once update function returns the success, the stop function is activated. So that is why you are seeing this stop message here. And it is showing the status invalid state was updated to the status success. So that is why the stop function is triggered and the terminate function is triggered. And since the sequence defines check battery function, once it's over, it moves to open gripper. The next function or action, open gripper, is activated. So you see the action is ticked, and the first, the initializer is activated under open gripper, and then the update function is triggered under open gripper. And as we are seeing, after 1 second, it returns a success. So the stop function is triggered under the action. And as I have explained, the status invalid is updated to the status success. And the terminate function is triggered. And the same thing, because now you finish the check battery, you finish the open gripper, so it move on to the approaching object. So that is why you are seeing after Open Gripper, you are seeing the approaching object. And basically the same thing is repeated. And once the status invalid is updated to status success, it will move on to the last action, which is closing a gripper. So this is very simple example. And what happens once everything is done? Once everything is done, you see finally the sequence is closed or stopped. Sequence stop, because all the children returns a success, 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 success. So the sequence is going to return the success and the program is finished. So that is what is going on here. Sequence is stopped. This is the first example. Let me move on to the next example. Simple demo 2. Probably you want to run this example in the loop. And in this demo 2, let me just first run to see what is going to happen. So basically, the tick once function is triggered under the loop. So it will run the loop for 20 times because this is 20. Yeah. So you are seeing this operation is continuously triggered for 20 times. Right, so it is finished. So let me explain what was done. In this case, the implementation is a bit modified. The relationship remains the same. There are 4 functions: check battery, open gripper, approaching object, and a close gripper. And this implementation is the same. The difference is, you can see there is another argument for the action. So what it means? Action, you can define another variable, which is max attempt count. So what this max attempt count does is, in the update function, you are going to decrement max attempt count function. So this attempt count function is initialized by the max attempt count. So basically the second argument is going to be input here. During the update function, always attempt count variable is decreased by 1. So that is why let's look at the open gripper. Open gripper action is initialized by the max count with 2. So what it means? So this function is going to be stopped under after the 2 loops, or after the 2 times execution. Because if not attempt count returns success. All right. So the first, it is 2. The attempt count is 2. But in the first loop, it will be reduced to 1. In the second loop, it will be reduced to 0. And basically, this if condition 0, if not 0, so not 0 means it is true. So if true, it returns success. Okay. So basically, the second argument is indicating how many times you have to run the loop. Otherwise, it will always return the running state. So let's look at what happened. In the first loop, the sequence is ticked because of the tick once function. And the check battery is first triggered. And the check batteries, I didn't explain, but the check battery function is the same. So it will always return success. So that is why after the first trigger, the status invalid will be updated to status success and it is terminated. Then it immediately moves to the next action, which is Open Gripper. And the tick function is triggered, initializer was triggered, and update. As I mentioned, so first the max count was 2. So in this case, it is reduced to number 1 and returns the running state, running. So in this case, it doesn't return success. So it will go to the next loop. So in the next loop, you can see the sequence is ticked again, and the action is ticked, which is the Open Gripper, and update function is triggered, which further decrements the max count or the attempt count from 1 to 0. And since it becomes 0, it will return success. So that is why you are seeing the status success here. And since the success is returned, it will terminate the action. Then go to the next action, which is approaching the object. When you look at the approaching object, what is the second condition, second argument? Second argument is 5, which means you need to continue the execution of this approach object action 5 times. So that is why you're seeing now first you triggered approaching object, yeah? And a second, you see approaching object, third, 2, 1. Or basically, you are decrementing 3 to 2, 2 to 1, and 1 to 0. So that is why the status running is updated for the status success. And then it will move to the cross gripper, right? In a cross gripper function, the argument is 3. So you will execute this action 3 times. You'll see the cross gripper function is triggered 1, 2, 3, and updated to status success, right? So in this case, the sequence is stopped because all of the children return the success. All of children return success, 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 and success. So in this case, the sequence returns success as well. So what happens next? So sequence is stopped, and then sequence is triggered again in the next loop. In the next loop, the sequence is ticked again, and you return the same thing. By the way, it is interesting to see in the next loop, like in the next bigger loop, which is to execute the sequence again. First, you see all the state is updated from success to invalid. Invalid is the initial condition, initial state. So that is why you are seeing this. Okay, so basically I'm talking about this area. All the success state is updated to invalid, success to be invalid, success to be invalid, and success to be invalid. You initialize the children action again, and then you start over. You start from checking battery, and it always returns the success, and it moves to the Open Gripper, blah, blah, blah. And you see, just speed up. So Open Gripper is 1, 2, and approaching object is 1, 2, 3, 4, 5, and closing gripper function is 3. Should be 1, 2, 3, yeah. And you start over. So it will be running 20 times, as I indicated. So this loop is executed for 20 times. So that is this demo number 2. Demo number 3 is not very significant. You can understand there is a function called the inverter. Inverter is defined under decorators, phi tree decorators. Personally, I don't think there is a huge demand for using this one, But let me just explain what the inverter does. So inverter can actually invert the logic of the action. Yeah. So very simple. If it is fail, it will return the success. What I meant is that this demo 3 is actually, it does the same thing as demo 1. There is no loop. It will run only one loop, like tick once. But you can see, and action and condition implementation is completely the same. And what's the difference? Difference is the use of the inverter. Inverter is inverting, oh, sorry, I made a mistake. Not the same. So you can see here, in the update function, it will always return the failure. It will always return the failure, the action. But this logic is inverted here by using the inverter function. So if any action always return the failure, by using an inverter, this action is actually returning the success always. Let me just run it. And this is what you have seen, exact the same in the example of demo 1. This is not very important or kind of trivial, I would say, but maybe you can understand what is going on here. Okay, so this is the basics of PyTree. I didn't mention the use of the selector and the parallel, but you will see in the next example in the PyTree ROS. So basically what you need to understand is the sequence, the use of the sequence and the selector and the parallel. And let me just briefly explain what selector does. So selector can return success by check, yeah, this is as written here. A selector executes each of its child behaviors in turn until one of them succeeds, at which point it itself returns running or success, or each runs out of children, at which point it itself returns failure. We usually refer to selecting children as a means of choosing between priorities. Each child and its subtree represent a decreasingly lower priority path. So, like, this is the difference between the sequence and the selector. So once when any of the children returns success, the selector returns success. So this is the basics of selector. And a parallel is, it has a multiple criteria. I think, yeah, this is described in, oh yeah, here. Success on all or success on one. So you can execute the several children in parallel, and you can actually define the behavior or the policy. So in this case, success on all or success on one or success on selected, here. I think you will see the use of this in the next example in the ROS. Right. So here, so far I have explained about the PyTree, and now we are moving on to the PyTree ROS. So this is a ROS2 implementation of PyTrees. And you can open this tutorial under the PyTrees ROS official website. And I'm gonna run some tutorial I selected. So the number 1, tutorial 1, number 2, tutorial 2, and the number 3, tutorial 5. So I think that's enough for you to be able to understand. And particularly, the most important thing is to understand the tutorial 5. So this is a kind of complex enough to implement your robot. So let's get started. First, you need to install the PyTrees ROS. So you need to go to the PyTrees ROS repository, and you have to run this command. And since this is using Jazzy, I changed it to Humble because I'm using Humble ROS. So I already executed this command, and I'm good to go. And in this example, you are actually installing the ROS Humble PyTree ROS tutorials, so you can run the command without compiling this command. So you can run the first tutorial, ROS2 launch PyTrees ROS tutorials 1 data gathering launch.py. So let me run it. So I'm going to open the ROS. Yeah, just let me clear console and let me run it. So it will open this interface, the GUI, robot mock. So this is a simulator. So we assume this is our robot, right? And with the monitor, some information is displayed. Yeah. And on this console, you can see some function is running. So let's move on to here. And this is how you can run. So I executed the first command. And second, you can run this command, PyTrees Blackboard Watcher. So some message are shown, like slash battery and some sensor message, and slash battery low warning is false. In this first example, you can just run how to use a Blackboard. So Blackboard is a kind of a global memory which can refer to from everywhere. By the way, you understand later. And let me run the next command, which is PyTrees Blackboard Watcher list. So Blackboard, as I said, this is a kind of a memory or the variable. And by the option list, you can list all of the available variables like slash batteries. Under this slash battery, you have a capacity, cell temperature, header, etc., which is very typical for the actual robot. And the last one, you can select only one variable, slash battery dot percentage. And as you are seeing, the battery percentage is decreasing. This is defined in this example. And let's see the implementation. So in this example, what is going on? So this is the basic example of understanding how we can use a Blackboard or BB. So BB, it's a Blackboard. As I said, this is a memory. So you can memorize the battery voltage and other variables. And here, so you have to understand this visualization. So this figure, this shape is meaning parallel, right? This square is a sequence. This is a selector. This is a sequence. This is a parallel, and this is selector. And this can be any other type of function. Yeah. So what is going to be done is, so first you have a parallel composite, and policy is success on all. So you have this parallel composite is going to run this and this, and it will wait until all the children returns success, success, and success. Okay. And the first sequence, topics to BB. So it means like it is sending the topics to the Blackboard. And sequence, although this is a sequence, it only has one child battery to BB. So it is writing the battery voltage to the blackboard. And particularly the sensor messages and battery low warning, right? Then let me see. Oh, so now you are seeing interesting thing. Battery percentage is currently 0, right? And then you can see the battery low warning is true. Battery low warning is true. Because in this example, when the battery percentage becomes less than 30%, it will trigger the battery low warning. Yeah. So I think let me run the program again. And let me run watcher again. So you are seeing now the battery low warning is false. You see? And you can actually manipulate the battery remaining voltage by the GUI here. And let me monitor 937, 36. As I mentioned, let's look at it. If this is less than 30, it will trigger the true. 32, 31, and 30, and now 29. Okay, here we go. So now it's true, right? So this is what will be going on. So battery low warning, when the battery is less than 30%, it will trigger the battery low warning. And you have another one, which is tasks. This is a selector. It is going to run the flip eggs and idle. So flip eggs is just a toy function to return running and success periodically. Like first, it returns running, and in the next loop, it will return success. So running, success, running, success. It doesn't have it doesn't have significant meanings, but this is just it like that. And so this is the implementation of this example. So first, you define the root, and it is a parallel, and it has a policy of success on all, right? And then you define the topics to BB as sequence, Topics to BB as sequence, yeah, here. And then you define a battery to BB. So this is using the function like pytrees rows battery to blackboard. And it is writing so yes, so it is monitoring the battery state. And so this is where you can define a threshold. By the way, you don't need to very serious about understanding this, because this is just a toy example. And this battery function is defined in the tutorial or the pytrees rows. So this is a pytrees rows function. So you don't really need to understand what is going on. Maybe you have to focus on how you can use a sequence and other composite and actions. Yeah. Then next, you define a selector. You define a selector tasks, and you define two function, which is to idle. So idle is returning running state always. Idle is always running returns a function. The running state. And the eggs flipper is it's a periodically returning the success in the interval of number 2. So meaning first you return running, and next you return success. Running, success, running, success. So this is what it meant here. And then you can construct your hierarchy. So you add child under the root. The first you add child topics to BB. So topics to BB is added, right? Topics to BB is added, then priorities is added. Priorities a child. I think priority is a selector. Yes. So this is the priorities and it is added. So this is how you can define the hierarchy or the tree structure. Good. Now so you are able to understand how we can use the Blackboard behavior function. So we can move on to the next one, which is to battery check. So the tree is a bit shifted, modified. And now you can see, well, I can just run the example and see. So let me run the tutorial number 2. So this is how you can run the tutorial number 2. So you have the same simulator. And let me run the watcher. Almost the same Blackboard memories. And you can monitor the battery percentage. So in this example, we can trigger some function once the battery low warning is triggered. So as I mentioned, the battery low warning is triggered when the battery becomes less than 30%. So you see, now the battery percentage is 27 and LED strip is blinking. Yep. So this is just indicating the low battery warning. And what happens, by the way, by clicking here, you can actually start charging your battery. So now it becomes 19, 20, 21, 22. It is charging, but still it is less than 30%. That is why the LED strip or the low battery warning is triggered. But maybe in 2 to 3 seconds, it will just returns to 30. Oh, by the way, I think you have to exceed 35%. Maybe this is a safety feature. So once it exceeds 35, you see the LED strip is no more blinking. And even you are seeing like battery low warning is false, right? So based on the state or the variable, which is battery low warning, you can actually trigger some functions. So this is what tutorial 2 is meant. And let me explain the state machine. So almost the same, but something is added here. Battery low. So this is using an eternal guard decorator. So it is monitoring the state of battery low warning. Yeah. And once it detects the battery low warning, it will trigger the flash LEDs. Like you see, LED strip was blinking here, right? So let me blink it. Yeah, LED strip is blinking. So which is to flash LED. Yeah. So this is just an addition. And let me explain how you can implement this. All right. So some differences. First, you have to define the flash LED function. There it is a predefined function under the ROSPy tree, so you don't need to implement. Yeah, you just instantiate it. And then the important block is here, like battery emergency is defined under the decorator eternal guard. And condition is check battery low on Blackboard. And this function is defined here. Yeah. And then battery low warning is a key. And so once it detects the battery low warning, it will trigger flash LED strip function. So this is how you can define the triggering the function. Yeah. Basically, that is only that the difference is. So I hope you understand. So let me explain. So this is a parallel. This is a sequence. And this is a selector. And sequence and the selector is running in parallel. And this sequence is always running the battery to BB function. Yeah. And when the 30%, I mean, the low battery is monitored, it will trigger this battery low decorator, and flash LED function is triggered sequentially, right? Good. So I hope you understand. Then the last one is tutorial number 5. So there is a significant addition of the state machine. Particularly, you are adding this block. Yeah, you are adding basically this area. Yeah, basically, it is related on the scan function. Yeah, maybe it's better to start running the example. So you go to below and you can run this function. So let me close and run. Yeah. And I also run this. Now you are seeing a bit of new function, which is event scan button. Yeah. This is a kind of new information. And you can, so now we can run the scan function. Yeah. So let me just run it. Yeah. When I press scan, some function starts triggering, and the LED strip is blinking first. And you may have observed the LED strip was blue, and once it's done, it becomes green. So like blue LED strip is blinking 1, 2, 3, 4, 5 times, and then green LED strips was blinking 4 times. Yeah. So let me explain how you are doing this. So first you need to understand this state machine. And basically you are also adding here. So the first sequence is monitoring two function or running the two functions sequentially. The first one is scan to BB, and this is monitoring if the function or the scan button is pushed. Okay, if the scan button is pushed, scan button, I mean here, and yeah, and when the scan button is pushed, it will actually send a message or the information to those two nodes. If the battery is low, this one is an eternal guard under the decorator, as you have seen in the, oh, sorry about that. Yeah, yes. Yeah, basically, yeah, it is connected to the battery. I'm gonna explain why later. And also the message or information is sent or connected to the scan function. So first, let me start. I wanted to also explain this one. Okay, good. So now it is low battery. So the warning is triggered. So now the battery level is 12%, 11%. Now, what happens if I push the scan button while low battery warning is activated? let me push it. Scan never happens. Yes, because it is reflecting the actual situation. So when the robot has low battery, you shouldn't scan because you don't have much power to finish this process. And interestingly, when you are seeing the event scan button, so let's look at it. Event scan button. Let me push the scan button. Boom. So now it became true, but the scan function was never triggered. So this is the point. So it is actually monitoring the scan button is pushed, but it never triggers the certain action. Yeah, because the battery is low. So this is how you can set the condition. So I was saying, so this pushing button detection is monitored by here. And if the battery is not low, it will run. Oh, sorry. I made a mistake. So I think, yeah. So I think we have to check the implementation of the battery low. Yeah. Battery low. Good. So if the battery is low, it will return the success because battery is low. And since this is a selector, it will return a success. So the following function will never be executed. So because yeah, this is just a blocking or preventing the scan function to be executed when the battery low warning is activated, right? Then now we can explain. So when the battery is full or battery is not low, you can actually execute the scan sequence. So scan sequence is activated by the scan button. Yeah. So this scan button, so let me look at it. Let me look inside this block. So under scan sequence, yeah, under scan sequence, this is the main sequence. Yeah. Under scan sequence, you have this node is scan requested. And it is checking the Blackboard variable value, which is a scan or event scan button. Yeah. And it will return true. It will return true or success when the push button, the scan button is pushed. Yeah. Then it will move to the next because this is a sequence. Once the success is returned, it will move to the next. Then it has a selector called the preempt. This is a bit complex, so let me explain one by one. So the first node under the selector is success is running. This sounds very weird, but this node does. It is overriding or overwriting the success state to running. So suppose this node returns success, but it never returns. It will be over. Oh, so I meant here, if the your children or child returns success, you wrap it as running. You see, if this returns success, it returns running. So success is running. So this is what this node does. Yeah. And So what is a node? Under success is running. So under success is running. Yeah, here. Under success is running. You have oh yeah. Under success is running, you have check Blackboard variable, which is the push button detection. Yeah. So in conclusion, if you press the push button, the scan button, it will activate this node and it will return the success. And once it receives the success, it will return the running. Yeah. So this selector is looking at it. And since it returns running, you go to the next, and it will trigger the scanning function, which is this is actual scanning implementation. This is a parallel, and the policy is success on 1. Yeah. And under this, the rotate and flash blue function is triggered. Actually, the flash blue LED always running returns running. So it basically it is waiting for the rotate function to return success. So let's see how the rotate function is implemented. But I think it is implemented in the next, the other file. So scan rotate is basically, yeah, this is what I meant. So PyTree's actions rotate. So maybe you need to check what is inside this function. But basically, it is, so you can understand this function is running a scanning function, like for 5 seconds. Maybe you can just imagine that you are using a LiDAR and it will take 5 seconds to scan some certain area. Yeah. And after the 5 seconds, it will return a success. So after, let's say 5 seconds, 3, 4, 5 seconds, it will return success, and it will return success, and it will return success. Then because this is a sequence, you can check the next one. And this is a parallel. The policy is a success on 1. And you see the pause function never returns success. So you are basically checking if when the flash green function returns success. So the condition of the flash green function is, this is here, flash green function is, flash green function never returns success, but scan pause function can return success. Yeah, it is a timer function. So after the 3 seconds, it will return success. So in the state machine, after 3 seconds, it will return success. So it will return success, it will return success, and it will return success. Yeah. So this is what is going on here. So maybe you may need to take time to understand this by running this, and maybe you can even change the code and see. Yeah. But with those examples, you can understand how you can use a parallel selector and sequence. Yeah. Yeah, that is it for the PyTree and the PyTree rows. Yeah. Okay, so in the another video, I'm going to explain the implementation of this demo program. Thank you.